Good day, ladies and gentlemen. I am Dr. Claudia Albers, Planet X researcher and professional physicist. And today I'd like to discuss with you another one of my articles, this one on a binary brown dwarf star system and also stellar evolution. The two objects shown in Figure 1 are part of the Lumen AB system, which is 6 light years away. And these objects are said to be brown dwarfs. However, from the image we can see that they are very close together and seem to be moving as one. And that they are surrounded by what seems to be a cloud of illuminated gas. Now, this cloud of gas that surrounds these two objects does not glow as brightly as the two objects, but it does glow. And therefore, this is an indication that this cloud of gas is experiencing plasma discharges and is therefore a cloud of ionized gas. Now, the brown dwarf stars in our solar system also have clouds of ionized gas surrounding them. And this cloud is left over from these stars going through the red giant and the white dwarf phases. This therefore indicates that these objects may just be brown dwarf stars, not brown dwarfs. Here we have a white dwarf star surrounded by the characteristic cloud of ionized gas, which is left over from the star's red giant phase. Now, according to accepted theory regarding star formation, brown dwarfs are substellar objects that simply did not have enough mass to become main sequence stars when they formed. In which case there is no likely reason for them to be surrounded by a cloud of ionized gas. So this cloud of ionized gas forms when a main sequence star stops being able to burn fuel. It therefore releases its outer layers of gas. It becomes a red giant and then it becomes a white dwarf. And this white dwarf is surrounded by an envelope of ionized gas, and then further out there is a more diffuse cloud of ionized gas. Now, another reason why these two objects, Lumen AB, are most probably brown dwarf stars is the fact that they appear to be equally bright. What we see here is the accepted theory of star formation. When a cloud collapses due to gravity attracting the gas cloud to one point. However, it is difficult to explain how this accepted theory of star formation due to gravitational collapse would lead to a binary system of exact equal brightness. In fact, having a binary system that's formed according to gravitational collapse is very difficult to explain. That is because gravity causes the collapse to happen to one point. But in order for us to have a binary system, we have to have gravity causing a cloud of gas to collapse to 2 points. And that is not easy to explain according to the gravitational collapse theory. And on top of that, it would be difficult to have two stars form that would at formation have exactly the same mass, so that a couple of million years later they would have exactly the same brightness. However, we know that the brown dwarf stars in the solar system are able to absorb energy from the sun. This is quite clear when we look at images from the SDO satellite, and we have some of these images here. This is from 2011, this one's from 2016, this one is from 2017. Now, the last solar maximum was in 2014, so 2011 was 3 years before the maximum. And 2017 is 3 years after. So we should have comparable brightness and activity on the sun, and yet we can see clearly that the sun brightness is much less in 2017 than it was in 2011. And this shows how the sun has grown so dim in this time, showing that it is being drained of energy. Now, the fact that the lumen AB objects are more likely to be brown dwarf stars rather than brown dwarfs means that possibly a lot of the brown dwarfs that are being studied that are 5, 7, 100 light years away may actually be brown dwarf stars. If this group is thought to be brown dwarfs, and when we examine them, they have the characteristics of brown dwarf stars because of the surrounding gas around them and almost exact luminosity of the two objects. Because in terms of what is happening in our solar system, we know that these objects are draining each other. So what would happen is if you have a binary star system and one would drain the other until they reach equilibrium so that eventually the two are equally bright. So this is what we have observed is happening in the solar system. These objects are draining our sun and it is becoming weaker and dimmer. So it is actually therefore very likely that a lot of the brown dwarfs that are being studied, and we are getting a lot of data, are actually brown dwarf stars. Now we do have, we've observed some of these objects, some of them through a telescope. For instance, the blue brown dwarf was observed very close to the sun, and here is a telescopic photograph of it. This was taken by Scott Sion through his small reflector. As you can see, it looks blue. It looks like it has pale yellow stripes on it. So when we first look at it, it may look like a brown dwarf. A brown dwarf can be blue with stripes, and then you would expect it to have a gaseous atmosphere, just like a gas giant planet. But when we looked at some more images of this object, it was observed that it had a solid surface. So it cannot be a brown dwarf. It has to be a brown dwarf star. Also, this object is obviously shedding large amounts of its last remaining gaseous envelope. And also, it wasn't emitting light. It was obviously reflecting light from the sun. And it had a solid surface. Now, where can we find a solid surface on a brown dwarf? It's not possible. Also, this object was outside the range of sizes expected of brown dwarfs because it was about 1/3 the size of the sun, which makes it 3.3 times the radius of Jupiter. And brown dwarfs are supposed to have a radius that only goes up to 1.2 times the radius of Jupiter. So obviously this was not a brown dwarf. This is what I call a stellar remnant. This object is a core of a star. And once upon a time, this star was a main sequence star, and it had a huge layer of gas on top of its core. In fact, this it would have been possibly 5 times larger than what the core looks like right now. And our sun at the moment also has a core. So as I have written before, main sequence stars are not likely to have fusion reactions in their cores. The reason for that is because our sun actually goes dark, and if we look at sunspots, they are dark and cool, which tells us that our sun, and therefore possibly all stars, are cool on the inside. This is very likely to be the case. We expect all the other stars in the universe to behave much like our sun. And if our sun is cool on the inside, then we would expect all other stars to be cool on the inside as well. So, and our sun goes dark, and that means that there is no huge amount of luminosity and energy coming from the center of the star, from its core. But I believe that stars do have fusion reactions, but it's happening on the surface. And they are powered by the electrical energy that a star has. So these are cold fusion reactions that happen on the star's surface. Then the material that is formed is denser and heavier than the material that the star is burning. For example, if it's burning hydrogen, it's turning it into helium. The helium is denser than hydrogen. It will sink down into the interior of the star and accumulate at the sun's core. Thus, the star would be forming a dense core at its center as it burns through its fuel. Then once the star's internal energy starts to drop, it would have more difficulty in ionizing its multiple layers of gas, and it will then start growing and going into the red giant phase and eventually turning into a white dwarf star. And during these two phases, the star would be shedding a lot of its outer layers of gas, and it will be left with a gaseous envelope, which is not nearly as large as the layers of gas it had as a main sequence star. And as the star's ability to ionize its gas drops and it loses a lot of its gas, it also loses much of the ability to power the fusion reactions on its surface. So its luminosity would drop. Now, the fact that the sun's energy is being drained by countless numbers of these stellar remnants, which are closely surrounding it, may lead to the sun being plunged into a premature aging process, which will see it start becoming a red giant. In other words, it would increase in size and it will become hotter. But it is possible that the sun will then not go through a complete red giant phase and a white dwarf phase, and this would be because these objects are draining it to such an extent that it's not even able to properly go into hydrogen fusion, and instead it will start losing the ability to ionize its clouds of gas. It will start losing its clouds of gas, and it will prematurely turn into a brown dwarf star without even possibly going through the white dwarf phase. Now, this may take many years. This may take 100 years or longer. It's hard to know because we don't actually have enough data about the sun's energy output or its ability to ionize its layers as these objects keep coming in. They have, I'm sure, been coming in for many years now, at least 30 years, but possibly 100 years. Now, a white dwarf star has a solid core which is made up of the less material it produced in fusion reactions. If the star was only able to burn hydrogen before it ran out of energy, then the core would be made out of helium. And if it was able to burn helium, this core will be made up of carbon and oxygen. And if it was able to end fusion reactions with the production of iron, then this would be for the larger stars, then the core would be made out of iron. In fact, we have a star that is large and orange. It's 26 times larger than the Sun. We see the size comparison here. This is Arcturus. And this star is turning into a red giant. Now, the fact that brown dwarf stars are much larger than white dwarf stars, and yet much weaker in terms of the magnetic field they are able to generate, and that this means that when they progress to the stellar remnant phase or the brown dwarf stage, they lose their gaseous envelope, and possibly provides a possible reason why stars become red giants, and that is because they lose enough energy to hold on to generate a large enough field, and we could think of it as the gravitational field, a magnetic field, or an electric field. In fact, it generates all three through its internal energy. And through its drop-off in energy, the fields it generates become weaker and weaker. So it finds it more and more difficult to both ionize its gaseous cloud, its gaseous envelope, and it finds it more difficult to generate mass. So its mass decreases, and its electric field decreases, and its ability to have fusion reactions on its surface will therefore decrease. And it will therefore grow. These stars can grow up to 400 times their original size. But basically that means that the layers of gas are moving away from the core of the star. And so this is the possible reason. And observing these brown dwarf stars in the solar system leads to this kind of understanding of what might actually be happening in the process that turns stars into red giants and white dwarfs eventually. So in conclusion, a profile for brown dwarf stars has been built up as a result of observing several of these objects in the solar system, and the 2 lumen AB objects fit the profile of brown dwarf stars. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.